Hello ladies and gentlemen, and welcome to Lecture 3. Here we're going to talk about the action potential. We touched on this a little bit in Lecture 2, and we're going to cover it in a bit more detail here. We're going to cover voltage-gated channels, in particular voltage-gated sodium and potassium channels. These are fundamental for generating action potentials. We'll talk about the passive properties of neurons and how they affect the change in membrane potential that we see in the action potential. And then we'll talk about refractory periods and myelination and how they affect the creation and conduction of action potentials. So the way that we change the membrane potential in an action potential is by quickly changing the conductance of sodium and potassium through the membrane. So we have voltage-gated sodium and potassium channels that will open and close very rapidly to allow sodium and then potassium to permeate the membrane. We should remember that sodium and potassium have very different reversal potentials, and as such will alter the membrane potential in very different ways. So the effect of these two ions on the membrane potential is fairly obvious whenever you use a couple different pharmacological agents to block them. So tetrodotoxin is a small molecule from pufferfish that will block voltage-gated sodium channels. So if you ingest enough tetrodotoxin, your neurons will no longer be able to fire action potentials, and when that happens, you don't live for very long. This is why it's very important that if you're ever having pufferfish, that it's prepared properly. And oftentimes the chef who's making it is required to eat some of the pufferfish. You want just enough tetrodotoxin that you get the taste of death, but not the actual experience of death. So people do eat tetrodotoxin, and on occasion they die from it, and that's because it blocks voltage-gated sodium channels. A normal action potential is shown on the top of this illustration there. You can see that the membrane potential is going to go from its negative rest to a positive potential and then back down and return to normal. When we apply tetrodotoxin, that normal action potential is now shown as a gray dotted line, and the response that you get in the presence of tetrodotoxin, you can see is now just a little hump. No action potential, no neurotransmitter release, no communication with our muscles, no more breathing. This is a very bad thing. Tetraethylammonium, or TEA, this is a voltage-gated potassium channel blocker. Now, remember, sodium reverses at positive 56 or positive 57 or so. So when you open a sodium channel, the membrane potential will move toward sodium's reversal. So the neuron is going to adopt a positive membrane potential. By opening up a voltage-gated potassium channel, you'll move toward potassium's reversal of minus 100, so you'll hyperpolarize. Whenever we block voltage-gated potassium channels, you see that the neuron can still depolarize because voltage-gated sodium channels are still able to open, but it doesn't hyperpolarize, and you can see that the action potential width increases here. So clearly, the voltage-gated sodium channels are responsible for depolarization. The voltage-gated potassium channels are responsible for the rapid repolarization and the hyperpolarization that we see in the action potential. And that means that change in membrane potential that we should all be familiar with as the action potential, where we go from negative to positive, then back, that's responsible, or that's created by first an early sodium current and then by a later potassium current. So you can see the conductance for sodium increases much more rapidly than potassium, and then potassium is much longer lived than sodium. This is why we get first a movement towards sodium's reversal, and then we have a movement toward potassium's reversal. Okay, so voltage-gated sodium channels are fundamental for action potentials. Without these, we don't have action potentials. Now there are two different subunits. There's the alpha and the beta. The alpha subunit is massive, and this actually creates the ion channel itself. The beta subunits are more regulatory subunits that can regulate the activity somewhat, but they also control the trafficking of these channels. So they make sure that they get in the right spot. They don't actually form the ion channel itself, though. So the beta subunits are very small. They're a single transmembrane domain, whereas the alpha subunits are going to be made of 4 different domains, each of which has 6 transmembrane domains. So 24 different transmembrane domains. Okay, the top illustration is showing you the cartoon where we have our alpha subunit with its 4 different domains forming the ion channel and a couple of betas on the outside. The bottom portion of this illustration shows you the beta subunit, but then it also shows you the alpha subunit. Now each of those gray cylinders is showing you the region of the protein that moves through the membrane. That's why we call it a transmembrane domain. It moves through the membrane. In a more useful cartoon format, here we have our voltage-gated sodium channels. You can see a top view and a cross-section view. Let's look below the cross-section view at the top view, and you'll see color-coded transmembrane domains. 1 is blue and 6 is red, then 2, 3, 4, and 5 transition. So we go from blue to red as we go from 1 to 6. And what you find there is transmembrane domains 5 and 6 from these 4 subunits actually form the ion pore. So they're located in the center of the voltage-gated sodium channel. These get pulled open when the activation gate, that 4th transmembrane domain, senses depolarization. And it can do this because of positively charged amino acids. So whenever positive charge enters the cell, this causes the 4th transmembrane domain to move, and that pulls on transmembrane domains 5 and 6. So let's look at the voltage-gated sodium channel in panel A versus panel B. What you'll notice here is that the bottom portion has been pulled open. So now we have an open ion channel, and that's because the 4th transmembrane domain has been moved by a change in the membrane potential. Voltage-gated sodium channels also have an inactivation gate as well as an activation gate. The inactivation gate would be the intracellular loop that's connecting the 3rd and 4th domains. So after the membrane depolarizes, the activation gate pulls open the ion pore, then the inactivation gate will actually stick into the ion pore to block it. So even though it's open, it's now blocked. And this is very important. Voltage-gated sodium channels inactivate. Okay, so the threshold potential is that potential at which we tend to find voltage-gated sodium channels open. So when the cell has been sufficiently depolarized to reach threshold potential, then that 4th transmembrane domain moves and pulls open the ion channel. When the voltage-gated sodium channels open, then our conductance for sodium dramatically increases. In other words, we're going to move our membrane potential toward the reversal for sodium. So we're going to approach positive 56. Okay, we probably won't hit it because before that, we're going to get some inactivation. But we're going to move toward it. So by opening up these sodium channels, sodium will enter the cell, and that entry of positively charged sodium is going to cause the membrane potential to adopt a positive charge. You'll notice that it's actually a depolarization that activates voltage-gated sodium channels, and that voltage-gated sodium channels lead to further depolarization. So when you have the activation of some voltage-gated sodium channels, that causes the activation of the rest of the voltage-gated sodium channels. And that's what makes our action potentials all or none. That's because they're activated by depolarization and they cause depolarization. So we can see in the illustration on top, we're looking at the activity of the sodium channel. Once we reach threshold, it opens. After it opens, the cell membrane is going to depolarize substantially and approach sodium's reversal. At time 3 there, you'll see that the sodium channel is inactivated That's because of that intracellular loop there that blocks it. And then we have no more sodium entry. That's going to allow for repolarization. So this illustration we're going to come back to several times here. The top is showing you the membrane potential, the middle is showing you the conductance, and the bottom is showing you a current. Okay, we can just look at the top and the middle, that's good enough. So that increase in sodium conductance, that's because we reach threshold potential and voltage-gated sodium channels open. Then the sodium conductance decreases because of inactivation. And that inactivation occurs because of that third intracellular loop that then bends up and sticks into the pore. So there's a little molecular hinge in the third intracellular loop that allows it to kind of flop around. And located in this hinge, we have some hydrophobic peptides that are going to stick into the pore. So they'll interact with other hydrophobic residues and just kind of remain in place. But in order for these hydrophobic peptides to stick, the pore has to be opened. So this is why inactivation will only occur if we're above threshold potential. Once we drop below threshold potential, then we can de-inactivate. So once the ion pore closes, it pushes out the inactivation gate. Let's have a look at our cartoon here again. So we're going to go from A to B whenever we reach threshold. We reach threshold potential, we pull open the ion pore. If you look at the top view, in A it's closed, in B it's open. In C, we can see the inactivation that occurs. Because the ion pore is open, that inactivation gate, that purple inactivation gate's flopping around, and that little ball there, those are our hydrophobic amino acids, and they stick in the pore only when it's open. Once we drop below threshold potential, transmembrane 4 goes back to its native conformation. It's no longer pulling open the ion channel, so the ion channel closes and spits out the inactivation gate. So that means after we pass our threshold potential, we have to then repolarize below threshold potential if we're ever going to have another sodium conductance through our voltage-gated sodium channels. So if we revisit this, we're at the portion of the action potential where we have hit the height of our voltage, and we're now repolarizing. And we're repolarizing because our sodium conductance has dropped off. Okay, this voltage-gated sodium channels are inactivating, and around this time you'll notice that the potassium conductance is increasing. This is because of voltage-gated potassium channels. They have a very similar structure to voltage-gated sodium channels, except they're not made of one polypeptide, they're made of several polypeptides. So it's not 4 different domains, it's 4 different peptides. Each of them have 6 transmembrane domains, very similar to voltage-gated sodium channels. Transmembrane domains 5 and 6 line the pore. The fourth transmembrane domain is the activation gate. But because this is made from 4 different polypeptides, there's no intracellular loop to act as the inactivation gate, and so voltage-gated potassium channels don't inactivate. Instead, they just open more slowly than voltage-gated sodium channels. And that's why we call them the delayed rectifier. Now, in this illustration, what we can see here, 4 different polypeptides, each with their own color: purple, yellow, green, blue. They're going to come together and form the ion channel. You don't need to know anything beyond what I've already told you. TMs 5 and 6 form the pore, and 4 is the activation gate. Let's see why it's the delayed rectifier. Look at that middle graph there, the conductance. The conductance is how much movement of ion there is, essentially, or how many ion channels are open. So when you increase the conductance, you increase the number of ion channels that are open. Notice that the sodium conductance increases much more rapidly than the potassium conductance. That's because these ion channels just open more slowly. They also close more slowly. So that potassium conductance comes on after the sodium conductance, and it remains elevated for longer. So it's delayed because it happens after, and it's the rectifier because it causes the membrane potential to rectify or to come back to rest. So first we have the opening of voltage-gated sodium channels. Sodium rushes in. The sodium channels inactivate. Potassium channels open. Potassium leaves, and the cell repolarizes. Because our potassium conductance is higher than at rest, we're closer to potassium's reversal, and thus we're hyperpolarized. And that's what creates that brief after hyperpolarization. Once we drop below threshold, the ion pores are going to close. This is going to both deactivate and de-inactivate voltage-gated sodium channels, and it will just simply deactivate our voltage-gated potassium channels. Our conductance returns back to resting conditions, and thus our membrane potential returns back to rest. So we're talking a lot about the movement of ions, the movement of charge. This is going to be affected not just by the opening and closing of ion channels, but also by some passive properties of the membrane. Okay, that would be the capacitance, the resistance of the membrane itself, and the internal resistance. All of these affect how charge moves throughout a cell. I want to touch on them quickly. I don't want to dwell on these. Okay, these passive properties do affect movement of charge, but I want to focus more on the active conductances here. Okay, at rest, neurons have relatively high membrane resistances. Okay, and that's because most ion channels are closed. The only things that are open are those leak channels that create the resting membrane potential. Because of this, because most ion channels are closed, very few ions permeate the membrane. So we have a low membrane resistance. That means that we have very few ion currents. When ion channels open up, we increase the conductance, and thus we decrease the resistance, because resistance is just the inverse of the conductance. Okay, so when those voltage-gated ion channels open up, we now have our leak, but we have the additional conductance through those ion channels. As such, the membrane resistance drops. Not only do neurons have high membrane resistance, because most ion channels are closed, they also have high membrane capacitance. Okay, and so the membrane is a capacitor. It does store charge, and that's because it's so thin. Even though it doesn't allow ions to move through it, it does allow ions to interact with other ions on the opposite side of the membrane. And that's just simply because the plasma membrane is so thin. That means that the charge interactions can still take place across the membrane. Now neurons, because they have so much membrane, because they have so much surface area, they have very, very high membrane capacitance. Now because the membrane is a capacitor, that means that any charge that moves through the membrane is going to first charge the membrane, and then it will affect the membrane potential. And this is going to cause those smooth transitions as we see. Okay? So the anions inside the cell, like those phosphates or some of the chloride there, those are going to be interacting with the positive charge, like sodium, outside of the cell. So we're going to actually have charge lining the membrane. So when we open up a sodium channel, sodium will rush in, but it won't freely diffuse throughout the cell. First, it's going to interact with those anions that line the membrane. And as we'll see, that slows how quickly the membrane potential will actually change. So because our membrane has resistance and capacitance, we view the membrane as an RC circuit. So there's a resistor and there's a capacitor. Okay, the lipid bilayer is the capacitor, the ion channels are the resistors. So the lipid bilayer will store charge, the ion channels will allow charge to move through the membrane. And of course, if you have an RC circuit, you need a battery, and that's going to be the sodium-potassium ATPase. So without the sodium-potassium ATPase to remove sodium and bring in potassium, we're going to eventually deplete the circuit. Okay, so the sodium-potassium ATPase keeps things going here. Okay. So whenever an ion moves across the membrane, the first thing it has to do is charge the membrane. Okay, so when positive charge comes in, it's going to first interact with those negative charges. It's not going to actually flow into the cell per se. It's first going to line the membrane. As it does that, what it's going to do is displace some of those negative charges that were lining the inside, and it's going to displace some of those positive charges that were on the outside, because the positive will repel the positive charges there. And that's going to create what we call a capacitance current. Okay, and we'll see that that capacitance current is going to actually subtract away from the input. So the more capacitance that a cell has, in other words, the bigger the neuron, the more slowly that the membrane potential changes, because it's going to create more capacitance current. All right, that charge is going to be stored at the membrane before it actually affects membrane potential. Once we charge up our membrane, then the ions will flow into the cytoplasm and actually change membrane potential. So let's have a look at capacitance here. On top, we're looking at injected current, and you can see that it's a square wave. We're immediately injecting about a quarter nanoamp of current, and then we're immediately removing it. But when you look at the change in membrane potential in the bottom panel, you'll see that it's curved. It's not a square. There's a slow movement to where it reaches the negative deflection in membrane potential. And whenever you remove the current, it doesn't immediately go back to rest. It gradually returns to rest. That's because of the charge that's stored at the membrane. First, we have to charge the capacitor whenever we inject the current, and then after we remove the current, then the capacitor still has that stored charge that it can release. So we have to then decharge the capacitor so that we return back to rest. Now, a lot of what we're talking about here can be summed up with Ohm's law. You should really be familiar with Ohm's law if you're going to understand membrane potential, and it's simply V equals IR. In other words, the amount of potential, that's V, is going to be equal to the amount of current times the amount of resistance. So when you increase resistance, assuming that the current remains the same, you'll actually build up more of a potential because you have that resistance that's going to allow the storage of charge. Conversely, if you reduce resistance, well, then you're going to have less of a potential difference because you now have free exchange of ions. So if we want to talk about currents, all we need to do is rearrange Ohm's law. Instead of V equals IR, it's I equals VG, or V divided by R, G being conductance here. So the amount of current that you get from a given ion depends on how far the membrane potential is from its reversal, so that's that driving force that we talked about last lecture, times the conductance. So if you're far away from the reversal potential and you open up a lot of ion channels, you should expect a big current. Okay, so here we're looking at the injection of current on top. Okay, but keep in mind, whenever we're looking at action potentials, like we're seeing on the right there, we're not really injecting current in real life. Not directly. Instead, what we're doing is just opening up ion channels. And so by opening up the sodium channel first, we get a big current that causes depolarization, and then by opening the potassium channels later, after we've depolarized, now we're really far from potassium's reversal potential. We have a big driving force. We have high conductance because the voltage-gated potassium channels opened up, and that's going to give us a big potassium current. Okay, Ohm's law is pretty powerful. So if you know the reversal potentials for ions and you know Ohm's law, you can figure out pretty much everything. Okay, it's a little tricky because of these passive properties, but really all they do is kind of smooth things out. Okay, so remember that injected current that we're putting in, that's always going to be a square wave, but the change in membrane potential that we get isn't a square. All right, it's going to be a smooth, kind of rounded transition. And that's because of membrane capacitance. We have to first charge our capacitor. Okay, so V equals IR, right? Your membrane potential is the product of the ionic currents that you have times the resistance. Okay. So in order for membrane potential to change, what we have to do is subtract that capacitance current from any of the injected current that we give. That's why the bigger the neuron, the slower the change in membrane potential, because of that membrane capacitance. Okay, and that's really what we're getting at here. If it's confusing to you to think about RC circuits or to calculate anything, don't worry about it. The bigger the neuron, the more capacitance, so the slower the change in membrane potential. That's really the take home here. Okay, if you're mathematically oriented, use the formula. If not, just remember, if you're big, you have more membrane to charge up, so it's going to be slower. Okay, because the membrane resistance and the membrane capacitance are both going to affect how charge enters the cell and how it moves around in the cell. Okay? Because when we're talking about the action potential, what we're talking about is the conduction of this depolarizing event down the axon. Because the whole point of generating an action potential is to release neurotransmitter from the axon. So really, this all boils down to moving charge around within a neuron. Okay? We want to create what we call axial current. In other words, we want those charges, once they enter the cell, to move throughout the axon. We don't want it to leak out the membrane. All right, that'd be bad. That would slow things down. So the ability to move this charge within the cell is dependent then on the membrane resistance and the capacitance. If we have greater membrane resistance, we have less leak. Therefore, we have greater axial current. On the other hand, if we have more capacitance, well, that means that we're going to lose some of that axial current by charging the membrane. Okay, the internal resistance is going to be determined by the diameter of wherever we're dealing with. Okay, the dendrites, because they taper, they're going to have different resistances depending on whether we're in the more distal or proximal portions. Okay, and that's going to affect how big of a potential we produce. Right? Remember, V equals IR. So the potential that we produce is a product of the current times the resistance. So on the left, we're looking at potentials in the distal dendrites relative to the soma. And on the right, we're looking at more proximal dendrites relative to the soma. Distal dendrites are much thinner. Therefore, they have a higher resistance, and so the potential that you get is much greater for the same amount of current. So if you look on the left, those distal dendrites create much bigger potentials than the proximal dendrites, even though they have very similar somatic potentials. So V equals IR. Okay, if you have high internal resistance, then you're going to hold that charge and have a lower axial current. Thus, you're going to build up more of a potential and create a bigger change in membrane potential. Okay, it's just that simple. If you have a potential, then you have a current. Okay, if you have a current, you have a potential. So if you increase resistance, that current isn't going to move as much, and the charge will get built up. So you'll have a greater potential. If you decrease the resistance, then that current can move, and you'll have less charge buildup, and thus less of a potential. So we can do a couple of simple calculations in order to estimate how this charge is going to move passively. So once we generate this depolarization by the action potential, how does it move around? Okay, how does it move in time and how does it move in space? So time is going to be described by the time constant tau. So once we have depolarization at a site, how rapidly do we reach maximal depolarization? Or conversely, when we repolarize, how long does it take to return back to rest? That depends on two things. It depends on the membrane resistance and it depends on the membrane capacitance. If you have a higher membrane resistance, That means you have reduced flow of charge. You have reduced currents. Okay? Therefore, it's going to take longer for the membrane potential to change. If you have an increase in membrane capacitance, well, that means that you have to store more charge before you start to affect the membrane potential. So both membrane resistance and membrane capacitance are going to create the time constant. So it's just simply a product of those two. If you increase resistance, that reduces your current, and thus it reduces the movement of ions that you need to create changes in membrane potential. On the other hand, if you have more membrane capacitance, then you have a bigger capacitor to charge. So you're going to steal away more of the charge to charging the membrane. So you'll have it'll take longer then to reach your maximal change in membrane potential. And this is why bigger cells respond more slowly. So the size of the cell then can affect the frequency of input that it responds to. Okay, and it has everything to do with the time constant. It's just membrane resistance, membrane capacitance. The movement of charge in space is described by lambda, the time constant. So once you have charge, how does it propagate? Does it move a very, very long distance before it dissipates to nothing, or does it quickly dissipate to nothing? And the space constant is going to be the square root of the membrane resistance divided by the internal resistance. So this makes sense. If you increase the membrane resistance, you're going to increase the space constant, which means that the charge can traverse longer distances because it's not leaking out of the membrane. On the other hand, if you decrease the internal resistance, that's also going to increase the space constant because you have less resistance inside the cell, and so that charge can move much longer distances because there's low internal resistance. Okay, so whenever we're generating electrical potentials, these are going to move in all directions in the cell, and they're going to move depending on the space constant, but also from the time constant. You should understand what capacitance is as a general concept. You should understand the difference between membrane resistance and internal resistance and how these two things work together to affect the movement of charge. Okay, we're not going to need to do any complex calculations, but you should understand that both time and space will dissipate charge, and the degree to which they do that depend on those passive properties of the membrane. Depends on how big it is, and depends on how much resistance there is. Okay. That being said, the propagation of action potentials is not going to be affected as greatly by those passive properties because this is actually an active event. We're actively generating action potentials. They're going to be shaped more by refractory periods and the degree of myelination. Okay, if you have a myelinated axon, this is going to actually increase the effect of those passive properties and thus allow very fast passive propagation of charge. Okay, more on that in just a bit. Let's first understand where we generate action potentials and why. Okay, here's a hideous cartoon of a neuron. The cell body's on top, surrounded by a couple of nasty-looking dendrites, and then we have a giant axon coming down the bottom there. The region where the axon connects with the cell body is what we call the axon hillock, and this is where we generate action potentials. We do this for two reasons. Okay, the initial segment of the axon there, right at the axon hillock, this is littered with voltage-gated sodium channels. As such, we can create a very strong sodium current. This is also a very thin portion of the cell relative to the cell body. So we're getting a bunch of input at the synapses in our dendrites, and that funnels into the cell body. It's very big there, so a very low internal resistance. But whenever we hit the axon, then we have a high internal resistance. V equals IR. So we have the same amount of current from our cell body now in a much smaller area. That increase in the internal resistance causes that same amount of current to create a much bigger potential change. So that the initial segment of the axon, because it has that thin diameter, it has that high internal resistance, and we get big changes in the membrane potential from the same amount of current. It's also littered with voltage-gated sodium channels. Here we're looking at a neuron cell body shown in red. It's just been filled up with a dye, sulfurrhodamine, and then they've stained with an antibody to show you voltage-gated sodium channels in green, and you can tell the axon hillock. You can see a couple of dendrites coming off of this red cell body on top, but then you see that one green process coming off of it. That's the axon hillock. That's where we generate the action potential because of all those voltage-gated sodium channels. Okay, if you like graphs, you can see on the bottom there's the soma, and then there's the initial segment of the axon that contains a whole bunch of sodium channels. And here they've actually just measured sodium conductance over time and space. So you see the robust red sodium current being only generated in that kind of initial segment, and then it drops off because of myelination. So there's going to be a limit to how quickly we can generate action potentials at this initial segment of the axon. And it's going to be shaped by the refractory periods. There are two of them. The first one is the absolute refractory period. It means that it is absolutely impossible to generate another action potential during this time period. That's because of voltage-gated sodium channel inactivation. Then we have the relative refractory period. That means it's relatively difficult to generate an action potential, but you can do it. You just need stronger input. That relative refractory period is caused by that after hyperpolarization. Okay, so if we're getting low stimulus intensity, that might be enough only to initiate one action potential. Okay, we're never going to initiate another action potential in that red absolute refractory period. But if we were to see a more intense stimulus, then we could create another action potential in the relative refractory period. It's a little more difficult, and that's why we need a stronger stimulus, but it's possible. Okay, it's absolutely impossible in the absolute refractory period because voltage-gated sodium channels inactivate. So before we have dropped below threshold potential and allowed the de-inactivation, it is absolutely impossible to create another strong sodium current. All right. So here we have our good old multi-part graph here showing you the voltage throughout the action potential and the sodium and potassium conductances and currents. Notice that sodium conductance is dropping off, and that's because of inactivation of the voltage-gated sodium channel. So once the inactivation gate blocks the pore, we must drop below threshold potential and allow de-inactivation. Otherwise, the pore is blocked. You can depolarize all you want, but you're never going to get a robust sodium current because of that inactivation gate. Okay, so this creates the absolute refractory period. No ifs, ands, or buts. You're never going to fire another action potential in the absolute refractory period. You must drop below threshold and de-inactivate your voltage-gated sodium channels. Now, this might sound like just a bad thing because it limits the rate at which we can conduct action potentials, but this is actually a very, very good thing because it allows the unidirectional movement of action potentials along the axon. Okay, so here's a little cartoon neuron shown in gray on top. You have the initial segment of the axon. The axon's running to the right. So once we generate that action potential, here we're going to look at our membrane potential where orange is kind of rest, green is depolarized, and red is hyperpolarized. So at the initial segment, we generate the action potential. Okay, we depolarize. It's green in this case. Charge is going to propagate in all directions. Okay, some of it's going to go back into the cell body because of that lower internal resistance, but plenty of it is still going to conduct along the axon. Then we have the inactivation of voltage-gated sodium channels, followed by the after hyperpolarization from the potassium efflux. Now, because voltage-gated sodium channels are inactivated, that passive depolarization that spreads from the next portion of the axon. So that is not going to be able to activate voltage-gated sodium channels. Okay, let's follow this action potential along from top to bottom. That's just showing you early to later. So at the very first moment, we have the depolarization at that very first initial segment. Then the charge propagates down the axon. It's going to sufficiently depolarize that section of the axon and open up voltage-gated sodium channels there. That depolarization also spreads in both directions, but the depolarization that spreads backwards on the axon is going to encounter voltage-gated sodium channels that are inactivated. So even though they get further depolarization, you can't have any sodium influx because of that inactivation gate. It's only after we repolarize and then hyperpolarize that our voltage-gated sodium channels are no longer inactivated. But at that point, the action potential has moved far enough down the axon that passive propagation of charge is never going to be sufficient to depolarize the de-inactivated sections of the axon. And this causes the action potential to move in one direction rather than reverberate back and forth along the axon. So the absolute refractory period is actually a very, very good thing. This allows us to generate one action potential and allow it to move the entirety of the axon without reverberating back and forth. The relative refractory period, on the other hand, is caused by the after hyperpolarization. Okay, remember, hyperpolarization just means we've gone more negative than rest, and that's because of the increase in potassium conductance. This after hyperpolarization is going to resist changes in membrane potential. So there's two reasons why it's difficult to generate an action potential. First of all, we're further away from threshold potential. So the hyperpolarization itself makes it difficult. That increase in potassium conductance also makes it difficult because as we depolarize, remember what that's doing to the driving force for potassium. It's going to increase it. So if we depolarize and create a greater driving force for potassium, that means we create a greater potassium current, and thus we resist movement away from potassium's reversal potential. So the relative refractory period is the time in which it's much more difficult to generate an action potential. You can do it, but it requires a very, very strong excitatory input. Now, myelination is going to increase the speed of action potential propagation, and it's going to do so by altering the passive properties of the membrane. Okay, so the myelinated regions are what we call internodes because they are between the nodes of Ranvier. The nodes of Ranvier are the unmyelinated regions that contain voltage-gated sodium and potassium channels. In other words, they have the ion channels. The internodes contain no ion channels, absolutely devoid of ion channels. As such, the membrane resistance is incredibly high. Now remember how this will affect the space constant. As you increase membrane resistance, the space constant is going to increase. Therefore, that charge is going to propagate over much longer distances without decaying. So the myelination allows the passive spread of charge to be sufficient to activate the voltage-gated sodium channels at the next node. We're also going to decrease capacitance, okay, by creating these layers and layers of fat around the axon, and by decreasing the membrane capacitance, we're not going to store the charge at the membrane. So this also causes a reduction in the loss of charge. So by reducing leak, by reducing membrane resistance, and by reducing membrane capacitance, what we do is allow a very efficient passive propagation of charge along the axon. And that creates this kind of leap of charge from node to node. It's what we call saltatory conduction. And that will dramatically increase the rate at which signals are passed along axons. You can feel the difference if you've ever bumped your knee. First, you'll realize that you've bumped your knee, and then you'll feel the pain. That's because the feeling of just touch, regular touch, non-painful touch, is conducted on myelinated axons. But the painful stimuli is going to be conducted on some myelinated and some unmyelinated axons. So you'll actually have two types of pain as well. There's the initial pain that comes on after the initial sensation that you've bumped, and then there's a long-lived pain. Okay, that has everything to do with myelination. So myelinated axons conduct signals much more rapidly. That's why we know we've hit our knee, and then later on we feel pain on those unmyelinated nociceptive axons. Alright, that covers it for the action potential. Email me any questions you have about the role of voltage-gated ion channels, whether they're sodium or potassium, in generating those changes in membrane potential. Make sure you understand the passive properties of membranes and how myelination affects those. Make sure you understand the difference between activation and deactivation. Make sure you also understand inactivation and deinactivation. They're very important concepts. Alright, I look forward to seeing you for Lecture 4.